Hello, my name is Alex Sherstinsky, and in this talk, we will take a look at recurrent neural networks and long short-term memory network from the perspectives of differential equations and signal processing. Numerous theoretical and experimental works have been published on the subject of recurrent neural network and the long short-term memory network, many of them reporting on the astounding results achieved across a wide variety of application domains, such as language modeling, speech-to-text transcription, machine translation, and other applications where data is sequential. The goal of this tutorial is to present the essential RNN and LSTM fundamentals from first principles. In particular, drawing from the concepts in signal processing, we will sketch the derivation of the canonical RNN formulation from differential equations. RNN unfolding or unrolling is a standard technique for evaluating recurrent neural networks. We will examine the RNN unrolling procedure as approximation of infinite length sequences by a series of shorter, independent, finite length subsequences or segments. We will then go over the well-known training difficulties, vanishing gradients, and exploding gradients, which arise when the basic recurrent neural network is trained using the gradient descent optimization method. The long short-term memory network, or LSTM network for short, was invented in order to solve the vanishing gradients problem. We will develop the LSTM network architecture by starting with a basic RNN architecture and use logical reasoning to add components to the system. We will then describe the constant error carousel. This is the mechanism by which the LSTM network circumvents the vanishing gradients problem. Next, I will introduce two novel extensions to the LSTM system architecture: the input context windows and the external input gate. We will conclude by summarizing the key takeaways and providing references for those who may be interested in exploring this material in greater depth. The main motivation behind the present work stems from the fact that oftentimes the key concepts, quantities, equations, and techniques associated with recurrent neural networks are stated as given. However, we show that they can be derived from first principles rooted in differential equations and signal processing. The long short-term memory network is the most popular type of the recurrent neural network. It has exhibited impressive benchmarks in a plurality of application domains. We provide a comprehensive theoretical coverage of the LSTM network, along with schematic diagrams aimed at gaining intuition. The overall style of this talk is qualitative rather than rigorous proofs. The emphasis is on logical reasoning and sketches of derivations. A more precise treatment is provided in the references given at the end of this presentation. Let us begin by deriving the formulation or the definition, as it is commonly stated, of the recurrent neural network. Our starting point will be a nonlinear ordinary delay differential equation with one discrete delay. Delay is a common feature of many processes in biology, chemistry, mechanics, physics, ecology, and physiology, among other fields, whereby the nature of the process dictates the use of delay equations as the only appropriate means of modeling. In particular, in engineering, time delays often arise in feedback loops involving sensors and actuators. In neural networks, the time delay is an intrinsic part of the system and also one of the key factors that determines the dynamics. In this equation, t denotes time in the continuous domain. X of t is the external input to the system. S of t is the state of the system, and R of t is the readout signal, which is obtained from the state signal via G, the warping nonlinearity. In artificial neural networks, traditionally, the requirements for G are that it is to be monotonically increasing and bipolarly saturating. Hence, the common choices for G are the hyperbolic tangent and the logistic function. The advantage of having the warping function with a squashing characteristic is that if the overall system is stable, then the state signal will be bounded. The time delay term tau 0 represents the memory aspect of this system. It enables the quantity holding the instantaneous time rate of change of the state signal, dSdt, to incorporate contributions from the readout signal that is measured at a different point in time relative to the current time t. Qualitatively, this temporal element enriches the expressive power of the model by capturing causal and contextual information. The matrix-valued coefficients A, B, and C, as well as the bias vector phi, are also the parameters of the system. The next step in our derivation is to employ the backward Euler formula with the sampling time step equal to delta t as the numerical integration method. By replacing all occurrences of continuous time t with its sampled version n times delta t, the differential equation turns into the difference equation that depends only on the discrete index n. Please also note that we set the delay constant tau 0 equal to the single time step delta t. This can be interpreted as storing the value of the readout signal into memory at every time step to be used as part of the update at the next time step. If we further scale the weight matrix coefficients and the bias vector as shown on the right, then we obtain the canonical recurrent neural network formulation. We call this first formulation canonical because the value of the state vector at the current step depends on the unwarped version of the state vector at the previous step. We will use this canonical formulation later to logically evolve the recurrent neural network architecture into the long short-term memory network architecture. The standard recurrent neural network formulation appears in the second equation, where the state at the current step depends on the warped state at the previous step. It does not depend on the unwarped state at the previous step. This simplified formulation makes it convenient for discussing the unfolding unrolling procedure and for stability analysis. Having arrived at the RNN system definition, we now proceed to the discussion of its computational aspects. A common technique used to compute the value of the state and other signals that are part of the recurrent neural network architecture is called the RNN unfolding, which is synonymous with RNN unrolling. These terms are used interchangeably. The computational problem is that the RNN is recursive. Using the signal processing terminology, it exhibits infinite impulse response. The solution is to unfold or unroll the recurrent neural network to a finite number of steps. As the name implies, this sequence will exhibit a finite impulse response. In addition to the cost-effective computational and storage characteristics of finite impulse response systems, a key advantage is that they are inherently stable by definition. Hence, from the signal processing viewpoint, the unfolding or unrolling is a technique for approximating infinite impulse response sequences with finite impulse response sequences as pertains to recurrent neural networks. The actual RNN unfolding or unrolling mechanism is equivalent to evaluating the recurrent neural network for a given finite number of steps. We start with an uninitialized RNN system as defined in this equation, repeated for convenience here. We then specify the initial conditions on the state signal. For example, 0 at index n equals -1. And then numerically evaluate the system for k discrete consecutive values of the index n. The members of the audience must be already questioning how a finite sequence can approximate a potentially long target sequence without placing restrictions on the number of samples and the alignment of the approximating sequence with respect to the target sequence. Indeed, the underlying assumption justifying the RNN unrolling procedure states that it must be possible to partition the ground truth target sequence into mutually independent subsequences. Then the unfolding mechanism is capable of providing a finite impulse response approximation to the otherwise infinite recurrent neural network model of the target sequence. In fact, if the assumption of mutual independence at the level of the segments of the target sequence is satisfied, then the RNN unfolding computation can be accomplished by the same reusable module. In the equations describing this prototype unfolded or unrolled recurrent neural network computational module, we use the tilde symbol to emphasize the fact that the registers used to store the indicated signals are reusable across all segments. It is important to point out that the input signal of the module x tilde has to take on all values of the external input x at every value of the index n, as n traverses every segment in any order thanks to the mutual independence of the segments. In all other respects, the form and the behavior of the prototype unfolded or unrolled RNN is that of the standard recurrent neural network. Let us take a step back and make some observations about the implications of using the RNN unfolding or unrolling procedure. In general, any infinite impulse response to finite impulse response sequence conversion is but an approximation with respect to some quality metric. It is not optimal in the absolute. The RNN unfolding procedure in particular truncates sequences thereby introducing artificial discontinuities not present in the target sequence. If the strict underlying assumption about the mutual independence of segments holds, then the unfolded or unrolled RNN model can be trained to track the actual sequence faithfully with respect to some merit criteria. Moreover, as we saw on the previous slide, the module that implements the unfolded or unrolled RNN model can process segments in any order and in parallel. However, if the target sequence is not amenable to being partitioned into mutually independent segments, then the truncation resulting from applying the unfolding or unrolling procedure will effectively undersample the target sequence. Essentially, the RNN segments of the unrolled model will appear too short and failing to fit any portion of the target sequence. The ramifications are that training will take a long time or fail to converge altogether, and inference will be plagued by distortion as compared to the actual signal. If the real-life data does not fully satisfy the fundamental assumption that justifies RNN unrolling, then it is reasonable to consider pre-processing the target sequence in order to achieve an empirical balance between the computational costs and the model efficacy. Assuming that the RNN unfolding is justified, we will now highlight the difficulties that arise during the RNN training phase. A recurrent neural network is trained by minimizing a cost function using the gradient descent optimization method and the backpropagation through time algorithm. Under a repeated application of the chain rule, the corrective gradient is propagated in the negative direction of the index n. This corrective gradient is used to update the parameters of the system, the connection weights. The issue is that the matrix containing the connection weights of the readout signal and the derivative of the warping nonlinearity appear in a multiplicative fashion at every step of the backpropagation. This implies that if all eigenvalues of the weight matrix of the readout signal are within the unit circle, or if the warping nonlinearity reaches a rail, then the corrective gradient going backwards in the sequence will be attenuated. As the corrective gradient vanishes, the connection weights cease to learn. On the other hand, if at least one eigenvalue of W sub r is outside of the unit circle, and if the warping function is biased in the middle, then the corrective gradients will grow out of bound. When an overflow occurs, the connection weights cannot learn either. As a consequence of using gradient descent optimization, the vanishing and exploding gradients problems hamper the training of the standard recurrent neural network. We just saw that the tight coupling between the readout signal and the state signal at the adjacent steps causes the vanishing gradients problem, which makes it difficult to train the standard recurrent neural network on long sequences. The long short-term memory network is a kind of a recurrent neural network that solves the vanishing gradients problem by introducing fractional gates in order to control the different contributions to the state signal. While the data signals are still warped by the hyperbolic tangent and produce output in the range between -1 and 1, the control gates are implemented using the logistic function in order to output fractions between 0 and 1. Just like the components of the data path signals, the control gates receive contributions from all available signals: the external input signal, the state signal, and the readout signal at the present and previous steps as appropriate. During the training phase, the parameter weights that control the drive input to the gates are learned together with the weights that shape the data path signals of the LSTM network. We will now evolve the canonical recurrent neural network into the long short-term memory network using logical reasoning. We start with the canonical RNN because, if you remember from an earlier part of the talk, it utilizes a contribution from the unwarped version of the state signal at the previous step, whereas the standard RNN system only utilizes the warped state signal at the previous step. We will identify the different terms that carry contributions to the state signal at the present step in order to work on them individually. We will pursue this along 3 main avenues. First, we will introduce 2 gates to control the contributions to the state signal at the current step from the state signal at the previous step and other update signals at the current step. Next, we will put a gate in the path of the readout signal in order to throttle the feedback between the readout signal at the previous step and the state signal at the current step. And finally, we will insert another hyperbolic tangent warping function into the data path in order to achieve a uniform dynamic range for all signals in the system. Looking at the canonical RNN system, we identify the different contributions to the state signal at the current step. The terms that directly depend on the state signal at the previous step, and the remaining terms which do not directly depend on the state signal. Let us give the first term the subscript S, as in state, and the second term the subscript U, as in update. And instead of mixing them equally, as in the canonical RNN system, we will mix them fractionally by using the respective gates. The state term will be multiplied by the control state gate. The update term will be multiplied by the control update gate. The accompanying diagram reflects the insertion of the control state gate and the control update gate for a richer mixing of the contributions by the corresponding components to the value of the state signal at the current step. The next modification to the canonical RNN system architecture focuses on adding control to the feedback portion of the update signal. This is accomplished by throttling the readout signal by the control readout gate to produce the system value signal V of n. The diagram depicts that the value signal, which is the readout signal throttled by the control readout gate, now contributes to the feedback portion of the update signal. Finally, in order to maintain a uniform dynamic range across all contributions to the state signal at the current step, we insert a hyperbolic tangent warping function in the path of the update signal. The figure illustrates the core equation of the LSTM network. It says that the value of the state signal at the current step is captured by two quantities: the state signal at the previous step as apportioned by the control state gate, and the update signal at the current step as allotted by the control update gate. In this schematic diagram of the complete LSTM system architecture, dashed rectangles and annotations are used to depict the function of each stage. We can follow this diagram from left to right in order to see the core LSTM network equation in action. The data update candidate stage mixes the external input at the current step with the system value at the previous step to produce the update signal U of n. The control update stage drives the control update gate, which will multiply the update signal for a contribution to the state signal at the current step. The control state stage drives the control state gate. It will multiply the state signal at the previous step as the other contribution to the state signal at the current step. And the control readout stage drives the control readout gate, which throttles the readout signal to produce the value signal V of n, which is stored so as to be used at the next step. Here is an example of LSTM computation unrolled to 4 steps. As the samples of the external input appear in the increasing order of the step index, the state signal is computed and propagated, thereby making the value signal available for external use. For instance, to be transformed into an output sequence. By taking another look at the central equation of the LSTM network, we can see that a mode of the system exists where the error gradient is propagated unattenuated for any length sequence. While all the other terms may vanish due to matrix coupling, If the control state gate is open, then the gradient with respect to the state signal will propagate as an unaltered sequence from one step to the next, theoretically indefinitely. This is called the constant error carousel and is the mechanism by which the LSTM network circumvents the vanishing gradients problem. However, it is important to point out that the LSTM network does not address the exploding gradients problem. That is usually remediated by gradient normalization. Over the years, a number of variations of the LSTM architecture have been introduced as a means of achieving certain objectives. We propose two novel extensions to the LSTM system: the non-causal input context windows and the external input gate. The purpose of the non-causal input context windows is to improve the system's capability to discern the context at the current sample via a look ahead into the near future samples of the external input signal if they are available. This is accomplished by extending the use of a single sample of the external input signal to the convolution of the external input signal with a non-causal matrix valued filter. The multiplication of the external input signal by a single matrix is replaced by the convolution of a dedicated matrix valued filter with the external input signal in every equation of the LSTM system that depends on the external input signal. The elements of the matrix valued filter coefficients comprising the non-causal input context windows are learned along with all the other system parameters during the training phase of the LSTM network. The other new LSTM extension, the external input gate, has to do with the composition of the signals making up the update signal. As we saw previously, the update signal is the sum of the system value signal, which is the throttled readout signal, and the external input signal in its entirety. The new control input gate, denoted as GCX, is applied to the windowed external input signal in the data path. The equalization of the external input signal and the readout signal facilitates an enhanced control of the update signal, which is aimed at improving the model's signal-to-noise ratio capabilities. The schematic diagram of the augmented LSTM system features the new control input stage and also highlights the convolutions of the external input signal with dedicated matrix-valued filters. We now summarize the material covered in this talk. We showed that the definition of the recurrent neural network can be derived from an ordinary nonlinear delay differential equation. It does not need to be stated axiomatically. The reason for taking the path of deriving the canonical Rnn equations from differential equations is that even though RNNs are expressed as difference equations, differential equations have been indispensable for modeling neural networks and continue making a profound impact on solving practical data processing tasks with machine learning methods. In fact, leveraging the established mathematical theories from differential equations in the continuous time domain has historically led to a better understanding of the evolution of the related difference equations. We then examined the popular RNN unfolding or unrolling technique from the signal processing perspective and concluded that it performs an approximation of an infinite sequence by a finite sequence under strict assumptions of the mutual independence of the subsequences comprising the original sequence. The long short-term memory network is a robust variant of the recurrent neural network. We derived the LSTM network by imbuing the canonical recurrent neural network with nonlinear gates. Finally, guided by the objective to broaden the expressivity of the model, we introduced two novel extensions to the LSTM system: the non-causal convolutional input context windows and the external input gate. The content of this talk was based on the first reference, which was published by Elsevier in the journal Physica D, Nonlinear Phenomena, in the special issue on machine learning and dynamical systems in March of 2020. I feel immensely honored and am extremely grateful for the opportunity to present to the esteemed audience at the second Symposium on Machine Learning and Dynamical Systems by the Fields Institute. I truly hope that the topics I covered are of interest to you. Thank you so much for your time and for your attention. I would be delighted to hear that the material we discussed has proven to be useful to you in your own research and development efforts. Thank you very much.